Kepler's ideas apply not just to planets, but to all orbiting celestial objects. And Kepler created 3 laws, and the first is the orbit of every planet is an ellipse, with the sun at one of the 2 foci. Kepler's second law says a line joining the planet and the sun sweeps out equal areas during equal intervals of time. Kepler's third law says the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. Before Kepler could derive his laws, ancient Greek astronomers came up with the geocentric model to explain how the motions of our planets worked. The geocentric model is explained by the scholars of ancient Greece imagining that the planets follow an ornate combination of circular paths with Earth in the center, as seen in the picture behind on this slideshow. The next system came along. I'm not going to pronounce it because I'll mess it up. And it explains the motions of the 5 planets. Each planet is assumed to move in a small circle called an epicycle, whose center in turn moves in a larger circle called a deferent, which is centered approximately on Earth. Both the epicycle and deferent rotate in the same direction, and this system came after the geocentric model, and the geocentric model was needed in order to describe the epicycle. Next came the heliocentric model, which was produced and created by Copernicus, and the model explains retrograde motion, and the retrograde motion of the planets is a result of our viewing the universe from a moving Earth. The heliocentric model is conceptually much simpler than an Earth-centered system, such as that of Ptolemy, which all its circles upon circles. Copernicus could determine the arrangement of the planets without ambiguity using the heliocentric model. Next in history came Tycho Brahe, who was around in the 1500s, and during his time, most scholars thought that the motions of the planets had existed in unchanging form since the beginning of the universe. However, he is the figure seen as a turning point in astronomical history in regards to what we've been talking about, due to his observations, and those observations show that the heavens are by no means pristine and unchanging. And from this, Johannes Kepler takes a good look at him and tries to create his own model. And so in the 17th century, Johannes Kepler took on the task of finding a model of planetary motion that agreed completely with Tycho's extensive and very accurate observations of planetary positions.
So Kepler's first law is that the planets orbit the sun, not in perfect circles, but in ellipses. And more importantly, the sun is located at one of the 2 foci of the planet's orbit. Now what this means is that its distance from the sun will constantly be changing because the sun isn't in the exact center of its orbit.
Okay, so Kepler, using observations of planetary orbits, was able to, using a lot of math that I won't go into, he was able to prove that on the elliptical orbit of a planet, the sun is located at one of the 2 foci, which means that at any given point in its orbit, a planet will be a different distance from the sun. But he was also able to prove that despite that, in the same amount of time, it'll sweep out the same area, which means that when it's closer to the sun, it actually goes faster, while when it's farther away from the sun, it'll go slower. I just wanted to show you how that we can prove that mathematically. So what we're going to do is we're going to make 2 vectors, right? So the first vector is going to be called r, and r is going to be the distance from the sun, the planet's distance from the sun, okay? Hopefully I can write that. Okay, so that's going to be vector r. Now the other vector is going to be delta r, and delta r is going to be how far the planet moves around its orbit. Okay, so those are our 2 vectors. Now what we're going to do is we want to know how big of a triangle that area is, like the triangle made by those 2 vectors. We want to know its area. And we know that a parallelogram made by 2 vectors is the area that is equal to the cross product of the 2 vectors. So what we're going to do is we're going to say A equals 1/2 of r cross delta r, which are our 2 vectors. Now what we can do is we can say Well, let's see how much that changes over time. So we're going to divide both sides, or multiply both sides, I guess you could say, by 1 over delta t. So we're going to have a over delta t equals 1/2 r cross delta r times 1 over delta t. Now what we can do is we can, using the properties of cross products, we can say, instead of having that, we can make it a bit prettier and say r cross delta r over delta t. Okay? So now what we can do, since we have delta t's in both of them, we can say this is equal to the change in area. So this is actually delta A. Probably should have included that. So it's delta A over delta t equals 1/2 r crossed with delta r over delta t. What we're going to do is we're going to take the limit of this as delta t approaches 0. And what happens is that as delta t becomes smaller and smaller, this actually becomes dA dt, or the derivative of area with respect to time, equals 1/2 r crossed with dr dt, which is the amount of area, the amount of distance it moves with respect to time. So that the derivative of that. And the funny thing is, dr dt is actually equal to, and which we all know, is equal to velocity. So we can actually turn this into r cross v, which is a lot nicer. So let's just do that. So now we have dA dt is equal to 1/2 r cross v. Now, the thing is that I'm not sure if you guys have learned this, but angular momentum, which is L, is equal to mass times the cross product of r times v. Or the cross product of r and v. So we know that. So now what we can do is we can say, well, we have an r cross v in our original differential equation. So we can say that L over m is equal to r cross v. So now we can take this r cross v and replace it with L over m. And when we multiply that by 1/2, we actually get L over 2m. So we have dA dt is equal to the angular momentum of the planet over 2 times its mass. Now the thing is that both of these values, both angular momentum and mass, are constants. So what we can surmise from this is that no matter where the planet is in its orbit, the change in area over time is going to be equal, and that's how Kepler proved that no matter where a planet is in its orbit, the area its orbit sweeps out is equal.
Okay, so lastly, with his third law, Kepler was able to prove that the ratio of the squares of the revolutionary periods for 2 planets is equal to the ratio of the cubes of their semi-major axes. And in this case, the period means the time it takes to orbit the Sun, and the semi-major axis is the distance from the planet to the center of its elliptical orbit. And this is really important because it shows why the amount of time it takes for a planet to orbit increases so rapidly with an increase in the radius of its orbit.
Some would argue today that Kepler actually started the scientific revolution because as a result, people started observing, experimenting, checking and calculating what nature was actually doing. And overall, Kepler's 3 laws of planetary motion provided the groundwork for many scientific discoveries. For example, Newton's work on universal gravitation, which we still use today in modern times. Kepler's laws are a landmark in the history of astronomy. They are extremely simple, and Kepler's laws made it possible to calculate the motions of the planets with more accuracy than any other geocentric model. His laws justified the idea of the heliocentric model. Also, today Kepler's laws are obeyed by spacecraft orbiting Earth, by galaxies in their orbits, and by binary star systems in which 2 stars revolve around each other.
aglow. My pen